So now I don't look at this till I need to make sure that this row and this row work well together. So what can you say about the function doing from 0 to negative 0.2877? It's decreasing. What should the derivative do if the function is decreasing? Be negative. Is it?
Yes.
Okay. Now, what does the function do from negative 0.2877 to 1.0986? So what should the derivative do? Is the derivative positive?
Yes.
This is how I check and make sure, or I find my mistakes. So we know now that when the derivative is negative, and then it becomes 0, which is the derivative, right? It's the tangent, and then it's positive. What type of point will this be? Minimum, right? There is no other way. So now I know that this is definitely a local min, for sure. Is it an absolute min? Look at the values, right? So it starts from 0, it goes to negative, and then goes up to positive. So this is not only local min, but also global. Good. Now let's identify what happens the rest. So one more time, it starts at 0, comes to negative, and then goes positive. So something like this. So what does this point say or do? Nothing. What does this one say? Global max. That's all. So 1 comma 1.0986, global max. Negative 1 comma 0, nothing. And this negative 1/2 comma negative 0.2877 is local and absolute min, or global, whatever you want. We use them interchangeably. And how come in an hour I didn't look at the screen at all? I have no idea. I know.
If it's both, can we call it global?
Okay. Good. Any questions on how to study a function on a closed interval? Do we need another example of studying the function on a closed interval? Yes?
Sure.
Okay. So, I'm sorry? I don't know if we're going to find any, but sure. Let's look at 51. You can choose 51, f of x, 3x to the fourth minus 4x cubed minus 12x squared plus 1, and the interval is negative 2 comma 3. So we have to determine the derivative. So f prime of x equals 12x to the third minus 12x squared minus 24x. This is our derivative. And then I'll get the table going. The first derivative is the first row after x, and the function is right after, immediately after it. The given interval, there is no discussion there. We can't do anything here. We can change that. So I hope you will agree that this function, the derivative, will never be undefined. It's a polynomial function, so there is no question there. Good. So the only critical numbers, if this function has critical numbers, they will come from setting it equal to 0. So then 12x cubed minus 12x squared minus 24x equals 0. I will definitely divide both sides by 12. So I have x to the third minus 12. I'm not sure why I wrote 12. I'm still upset about that. Nothing to do with you. I shouldn't. Okay. So x squared minus 2x equals 0. How many solutions do we expect? definitely 3. I will factor out x, and I get x squared minus x minus 2. So then x minus 2, and x plus 1 equals 0. As expected, 3 solutions. First one is x equals 0, x equals 2, and x equals negative 1. Now we'll see which values are present, which x values are, they're all critical numbers, of course. So let's see which ones fit in the interval given to us. If all of them, then all of them. So 0, yes. 2, yes. Negative 1, yes. So all 3 are in there. At this point, I will have to determine 1, 2, 3, 4, 5 values. I will put f of x in the graphing calculator. So let's do just that. So 3x to the 4th, then minus 4x cubed, then minus 12x squared, plus 1, thank you so much. So with second and table, I will plug in negative 2, then I will plug in negative 1, then I will plug in 0, then I will plug in 2, and I will plug in 3. So I have all those values: 33, negative 4, 1, negative 31, and 28. Any questions so far? Any questions? Okay. Now I would like to study the sign of the derivative. The derivative is, careful, we did not lose anything by... Okay. Sorry about that. Sorry about that. Is it still? Okay, it did. I pressed it, but not enough. So, when one thing goes wrong, then watch me. Okay, so careful, because sometimes when we solve the equation, we may divide by a negative number, and that will change the problem. So this is still the same thing with just a 12 in front, right? So if I want to rewrite this, will be 12x and the whole thing. X minus 2, x plus 1. So now, I'm going to try to identify, this is very important for what happens next. You can say, I really don't care about the derivative. It's a sign of the derivative. I can already tell. This is the absolute min, this is the absolute max, goodbye. True, but this is what I need for the next sections. So let's do that. So what I'm going to do is, I'm going to put this function, because these are so close, right? So when I plug in 1 in here, positive, positive, negative. So I know that this portion will be negative. You agree? I picked 1 between 0 and 2, positive, positive, negative, positive. But now here with 2.5, it becomes a little bit cumbersome. With negative 0.5, it becomes a little cumbersome. Or with negative 1.5 becomes a little bit cumbersome. So I'm going to put this as a different function in the calculator and just study the sign. So go back to y equals, and I have 12x. I don't need the 12, but I'm going to put it in. X minus 2 and x plus 1. So I plug in those values that I was mentioning. So negative 1.5, oops, negative 1.5. Then I wanted negative 0.5. And I also wanted 2.5. So for negative 1.5, what is the sign of the derivative? That's all I care about. For negative 0.5, what is the sign of the derivative? And finally, between 2 and 3, at 2.5, the sign of the derivative is positive. This is the moment of truth in which I catch my mistakes, just in case. What does the function do between 33 and negative 4? So what will the derivative have to do?
Should be negative.
What does the function do between -4 and 1? So what should the function do? What does it do between 1 and -31? Is this true?
Yes.
Supported by the sign. And between -31 and 28, increase. So that's when I realized that if something is wrong, that's how I catch my mistakes. By making sure that this row for the derivative works well with the row of values for x.
So if you get something like where it's negative but it's going up, like there's something wrong.
Yes. So if I have, for example, here, let's say 40, from 33 to 40, the function is increasing, but that's not supported by the sign of the derivative, then I know something is wrong. Or this is correct, but I get positive here. Then I said, oops, from 33 to -40, it's decreasing. How can the derivative is positive? That's not possible. So finally, let's just picture the idea here. So this is up here at 33. This is down here at -4. This is 1 here. I'm not graphing the function. I'm just plotting the points. So this is -31, which will be here, -31. And then 28 is somewhere here. So what can you say about 33?
It's a global.
Global max, is it a local max?
No.
No, because it's at the end point of the interval. So I'm going to write in a minute, -2, 33 global max. Is there anything that I could say? I could only say that -1, -4 is a local minimum. Local minimum. Why? Because that's typical. Negative, 0, positive. So this must be a local minimum because of the sequence of the signs. The derivative changes sign. Okay, 0, 1. It's up and down, right? So this will be a local maximum. Perfect. What about 2, -31?
Global.
It's going to be local minimum, but also global. Correct. And what about 28?
Nothing.
Nothing. That's the analysis for this function. So now I'm going to put them in writing. So -2, 33 global max. -1, -4 local min. 0, 1 local max. 2, -31 local and global min. And 3, 28 nothing. Is this clear now concerning studying a function on a closed interval? Perfect. Yes?
The ends of the interval are always
Either nothing
assessed as
or
well.
global max or global min.
But even if they're not critical numbers, we
Yes.
check them.
Awesome question. Here's why. Because I'm asked to study the function on a closed interval. If I'm asked to study the function on its domain, it's a different story. But I'm specifically told, study the function on this interval. Then you have to look at those endpoints. Very good question. Thank you. Okay. Section 4.2 is important. I will not forget about it. But I will, since I have you here and we're already in the clear for what we're trying to do, I would like to skip for now, and I'm going to cover it next week. Okay, section 4.2. So I'm moving on to section 4.3. So 4.2 next week. In 4.3, we are going to study how derivatives affect the graph. Or what does, in other words, in short, what do f prime and f double prime say about f of x? This should have been the real title. What do f prime and f double prime say about f of x? What do they tell us about f of x? Okay. One thing that we already know, but I didn't tell you what it was, is when we study the derivative, there are several possibilities. Let's say the derivative is 0, and the sign changed like this for the derivative. What will that point represent? A max. Very good. What if the derivative is 0, but the signs of the derivative change like this? Min. What if the derivative is 0, but we have this? What will that represent? Nothing. Although this is a critical number, because the derivative does not change sign.
So it's like x cubed.
It's like x cubed, which is an inflection point. We're going to get to that in a minute. Okay? So if the signs do not change, even if there is a critical number there, this does not represent a max or min. So here's another situation. What do you think about this? Exactly. Nothing. What do you think about this? No. This is when the derivative is undefined.
No.
Careful.
It's a max.
It's a max.
Indeed. Why is it a max?
The two
Because
values.
because this is the critical number coming from f prime being undefined when the function is defined. So I should have mentioned that at this point the function is defined.
I see.
What about this?
Min.
He had it with me. Okay. What about this?
No.
Nothing.
And last
No,
option.
Nothing.
My goodness.
What do you have written here after the?
Min,
Nothing.
That's just
max,
like
min,
same thing.
nothing is the same. I didn't want to copy it. I was too lazy. And then max, min, nothing, and I didn't want to copy it. Very good. This is called the first derivative test. This is what it's called, the first derivative test, in which we determine max, min. Okay, I want to practice one more problem here. On page 299, we're going to do this in 2 stages, or you want to talk about the second derivative test before, because I can't find a problem, but we can do it in 2 stages. I can't find a problem that focuses only on the first derivative test. Okay. Oh yeah, we can just choose one and just do part of it, and then we'll come back to it. Okay, let's do another polynomial function. Let's say 35 on page 299. F of x equals 2 plus 2x squared minus x to the 4th. We are asked few things here. I'm only going to read the first 2. Find the intervals of increase or decrease. We're going to be able to determine that in a minute. Find the local max and local min values. We're going to be able to determine those using the first derivative test. Okay, so this is a function. It's polynomial. I will get my table going with negative infinity to infinity. No one restricts this in any way, shape, or form. This is the entire domain. Always, please, if you'd like this chart, please use it. If you want to invent your own, I'm fine. But the function should, if you're using this, the function should always be in the middle. The first row should be the derivative, the middle row should be the function, and the last row should be the second derivative. Okay. My next step is to find the derivative. Very good. So f prime of x is indeed negative 4x to the 3rd plus 4x. Perfect. I will definitely factor out negative 4x, and I have x squared minus 1. I will continue factoring. How do I factor? Oops. How do I factor now?
X minus 1, X plus minus 1.
Good. So what are the zeros of f prime? Obviously, it's always defined. There are no critical numbers coming from f prime being undefined. So what are the zeros of f prime?
0, 1, negative.
Very good. In this order, negative 1, 0, and 1. 0, 0, 0. In the next step, like before, I'm going to determine these, but this we haven't done yet. And you're going to tell me what that means. So in the function, I will plug in negative 1, which is not difficult, right? So negative 1 with 1, it's symmetric, so it's going to be the same number. So 2 plus 2 is 4, and 4 minus 1 is 3. I hope you agree that this is 3 and this is 3. And with 0, this is 2. Is that okay? We plugged in the numbers in the function. Which numbers? The critical numbers to determine the values, the y coordinates. Why? In a minute, you'll see why. So what am I pointing here at? What am I really asking you to tell me here and here?
The local.
Directions.
Correct, but how do I determine that? Thank you very much. The limit of the function as x approaches negative infinity and the limit of the function as x approaches infinity. In pre-calculus, I was telling my students it does but now I'm going to say nope, because we studied limits. So what is the limit of this function when x approaches negative infinity? Which of these three terms counts at infinities? Negative, careful, negative x to the fourth. So when x approaches negative infinity, negative x to the fourth will dictate. Not when we talk about anything else, but only at infinities, this is the one that dictates. So where will this go? Do you all agree with negative infinity? Because whatever to the fourth will be positive with minus in front will be negative. So this is definitely negative infinity. What about for positive infinity? Good.
Would that be for the... Oh, my bad.
Good. So now, I need to study the sign of the derivative. Well, that's not a difficult task. So I'm going to plug in negative 10. Negative, 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 and another negative. What will be the sign? Now it's a little bit more tricky because I have negative 0.5. I can plug it in and so on and so forth. But definitely on the other side will be positive, positive, positive with negative. So now in here, I have to figure out the signs. So with negative 0.5, this is positive, this is negative, negative, and negative. 1, 2, 3.
Negative.
And on the other side, I think it's going to be positive, but let's check. So with 0.5, positive, negative, positive, negative. Now is the moment of truth in which I make sure that these two rows communicate well. So I know I have no mistakes. Let's try. From negative infinity to 3, what does this function do? Right. Is that supported by the sign of the derivative? Yes. From 3 to 2. Down. Is that supported by the sign of the derivative? Correct. So from 2 to 3. And it's supported by the sign, and from 3 to negative infinity. So all our calculations in row 1 and row 2 are correct. Okay. So now if we are asked, which I will not, because once you have this, for me, is good enough. But the problem is asking us, what are the intervals of increasing? Well, obviously, the intervals of increasing are negative 1, union. That's where the derivative is positive. Now the question is, what are the intervals of decreasing?
Negative 1 to 0.
Because the derivative is negative, union.
1 to infinity.
1 to infinity. Is that clear? Okay. Now let's establish what these points represent. -1, 3. What does this represent?
Like global and local.
We can now no longer talk about global.
Okay, so it's just
So
local.
it's a very good point. Thank you. Very good point. So when we talk about a function max min on its domain, we have to look at the graph mainly. So you can say, oh, I see, it's definitely fine, it's possible. But I would recommend before you decide about global, you may want to look at the graph. Local is no problem. Local is no problem. In this case, I would say global is no problem because there is no other number larger than 3. So obviously there are 2 global max. So -1, 3, because of the change of sign and because it's a critical number, I will write underneath it's a local max for now. And then later on I can identify globals. Okay, what type of point is 0, 2? Indeed, a local min. And what about 1, 3? Local max. So that's absolutely clear. Now, let's continue because the problem is asking us find the intervals of concavity now and the inflection points. So that's our next step. And then we'll come back to the problem because it's not finished. And then we'll graph the function. Okay. When the second derivative is 0, at those points that make the second derivative 0, the function may have inflection points. What is an inflection point? An inflection point is when a function is opening down, and at some point, no max min, at some point it changes by opening upward. We know this from x cubed. X cubed does this. So it's concave down on this side and concave up on this side. So that's concavity. Concave downwards, concave upwards. That point where that happens, the second derivative must change sign. If it does not change sign, that's not an inflection point. So for this function, let's determine the second derivative. We have the first derivative, which is here. I will continue differentiating the second time. So -12x squared plus 4. I will set this equal to 0. I will divide both sides by -4 even. So I have 3x squared minus 1 equals 0. Then I will get x squared equals 1/3. And I cannot forget to put plus or minus the square root of 1/3. Now, when things get a little bit more complicated, so let's take the square root of this. So the square root of parentheses 1 divided by 3. And I got 0.56. I hope you agree. So x equals plus or minus 0.56. Oops. Right? I have to put them in the table. So -0.56 and 0.56. I have to determine this value right here and this value right here. It's going to be the same because the function is even. We'll talk about it in a minute. So I will plug it in. So 2 plus 2 multiplied by the previous answer squared, and then minus the previous answer raised to the 4th power.
Where'd you get the equation you're doing now?
So I'm
Gotcha.
plugging in f of x. I'm plugging in these two values to determine the y coordinates for these 2 points. Okay, and I got 2.55. Let's say 2.56. So 2.56. 2.56. 0 here and 0 here. I have to study the sign of the second derivative now. And this is the second derivative. Let's plug in 0. When I plug in 0, what will be the sign of the second derivative?
Positive.
Very good, awesome. Now let's plug in 10. 100 times negative. Let's plug in negative 10.
Negative.
Okay, so here is our conclusion. When the second derivative is positive, the function, we say, holds water. I put a sign right here. When the second derivative is negative, the function opens downward. Does not hold water. What do you conclude about the point, because the second derivative changes sign, what would you conclude about the point negative 0.56 comma 2.56? That is called an IP, inflection point. Okay, the same thing here because the second derivative changes sign. So this will be an IP. Finally, let's talk about the second derivative test. I personally very rarely use it. I don't have anything against it. It's a very good test. Let me tell you what it says and what it does. I apply it when I find that studying the sign of the first derivative is difficult. So let's suppose, don't erase anything because I'm going to write it again. Let's suppose, for whatever reason, I decide not to determine the sign of the first derivative. I don't want to, for whatever reason. Here is the assessment. So when at the point where the first derivative is 0, if the second derivative is negative, what should the signs be here? One more time.
Say the question again.
Yes. So when the first derivative is 0, the first derivative is 0 at negative 1. But I know that the second derivative gives me the indication that the function is opening downwards. What kind of point will be negative 1 comma 3? And what will be the signs left and right of the first derivative?
So Max said positive, negative.
That's it. That's the second derivative test. Let's take a look at the other critical number. 0 comma 2, right? When x is 0. Let's take a look. So the second derivative is positive, which gives the indication that the function has what?
A minimum.
Right. So what will be the signs here, left and right?
Positive and negative.
Careful.
Negative, positive.
Right. So this is a second way of determining the signs of the first derivative instead of plugging numbers in. Last one. We have 1 comma 3. It's a critical point because the derivative is 0. 1 comma 3. So now the second derivative gives the indication that is opening downward. The function opens downward. So then,
Positive.
what are the signs of this?
Positive.
Positive and negative. So this is how the second derivative tells us, gives us information about the function. So I personally prefer to determine the sign of the first derivative and not wait for the second derivative. Here's why. Sometimes the second derivative is so difficult to determine that I'd rather not determine it. So then I still have to rely on something. Yes, Ellie?
Are you ever going to make us use one or the other?
No.
Or do you always let us pick?
It's up to you. It's up to you. I think that the second derivative test is a little bit more difficult than the first derivative test and finding the sign of the first derivative. But it's fine. So this is the second derivative test. Now, we have all information except the x-intercepts. We have not determined the x and the y-intercept for this function. So it happens that 0, 2 is a critical number and also the y-intercept when x is 0, but I have not determined the x-intercepts yet. How many solutions do I expect? It doesn't mean that I have to have 4. Yes. So we have to solve the equation f of x equals 0 to determine the x-intercepts. And then we are ready to graph this function, and there are absolutely 0 secrets about this function. We know absolutely everything about it. But we have to determine the x-intercepts. We determine the limits. We determine everything. And the symmetry, which we know, obviously, when I replace x by negative x, nothing is going to happen, so the function is even. So let's solve the equation. Negative x to the 4th plus 2x squared plus 2 equals 0. Or x to the 4th minus 2x squared minus 2 equals 0. This is not going to be an easy task. Even if you notice that this is quadratic in form and you replace x squared with a substitution, it's not going to be an easy task. So we will end up having to use a calculator anyway. So let's use the calculator and find the x-intercepts. So let's just put in the function in the calculator. Let me do it up here. So do I have the function in there? No, this was a different function, right? Yes. So I have negative x to the 4th. And then plus 2x squared. And then plus 2. And I only want to determine the zeros. So I'm going to use this Zoom 6 and then go to second and calc. Second and calc. And I want the zeros. 0, number 2, the zeros. And the left bound, I'm going to put negative 3. The right bound, I'm going to put 0. Just give me the x-intercept. I don't want to guess. So it's negative 1.65. Okay, so I'll go back to my chart. Negative 1.65, and this is 0. And the other one will be a 1.65 because the function is even. Now I would like to go slowly, look at the chart, and graph the function. You can say, well, we already saw the function. True, we did, because I had to use the calculator to find the x-intercepts. But I want to show you how all this comes together when we graph the function. Ready? Okay. I'm going to start a new page because I only need this. I don't care for anything else. This is the only information I need now. So here's the coordinate system. I will have to start by plotting the points I have. I have negative 1.65, so 1, 2, 3, 4, 5. I have negative 1.65. So right here, 1, 2, 3, and 1.65. Then I have negative 1, 3. Then I have 0, 2. Then I have 1, 3. And that's it. Now, I also have negative 0.5 to 2.56. Negative 0.5 to 2.56. And on the other side. Ready? Let's do this together. Watch the first time, and then you'll understand, and you can copy it. And I can repeat it. I can do another graph one more time. Okay, from negative infinity, it's increasing, opening downward till this point. It continues to increase to negative 1, 3, still opening downward. Now at this point, it starts decreasing to this point of inflection, opening downward still. It's at this inflection point where it has to change concavity, still decreasing, but now opening upward to this point. Still opening up, but now increasing to this other point of inflection. For now, I can already copy because it's an even function, but let's continue. So the point of inflection, 0.56 to 2.56. So now it's still increasing, but all of a sudden it starts going up and down because this is an inflection point. Go to the maximum of 1,3, and then decreasing, crossing, going to negative infinity. We couldn't do this in pre-calculus because we were not able to determine inflection points. We didn't even know what they were, and we could not determine max min without a calculator. We determined the max min without the calculator. The only thing that we had difficulties with was here, finding the x-intercepts. But everything else was determined by hand. So f of x equals negative x to the fourth plus 2x squared plus 2. And this was possible only because we were able to study the first derivative and the second derivative. One more time, what does the first derivative say? When the function is increasing, when the function is decreasing, and when it has a max min. What does the second derivative say? When the function has inflection points and when it opens upward or downward. Studying and putting all them together gives us the graph. Again, as you know, I do not have any problem with the way the book presents everything. But let me just show you what they show. Without, in my opinion, again, this is not a criticism. This may work for some. This may work for some. But I will not be able, without presenting or organizing my information, I will not be able to put it together. So here it is. They start here with a domain. They go to A, B, C, D, E, F, G, H. And there is no, they're just coming up with a graph. But there is no summary. I mean, how can this may be on 2 or 3 pages. How can I put this together and come up with that? The same thing here. So they start with this, and they calculate stuff, and they say it's this. And they said, since f prime is greater than 0 when x is between -2 and 0, and the first derivative is less than 0 when x is between 0 and 2, f is increasing on this and decreasing on that. So again, there is no criticism, but I think that without summarizing all the information, but they do summarize once in one problem, which is this. See you on that and see it's concave up, concave down. So, and then they come up with a graph. So again, if you don't like this, invent your own. So you can summarize the information so you can put it all together. Any questions? Any questions? Okay, so now let's choose another problem and go through all these steps one more time.